Good afternoon, dear students. Today we are going to discuss about ion exchange chromatography. See, ion exchange chromatography is a process that allows separation of ions based upon their charge. Okay, and usually any molecule, a large or a small molecule like a protein or a nucleic acid or a amino acid, can be separated by ion exchange chromatography. The mobile phase used generally is a buffer whose pH is important as far as separation of charged molecule is concerned, and the stationary phase is generally a resin. Okay, let us start. Ion exchange chromatography. Ion exchange may be defined as reversible exchange of ions in solution with ions electrostatically bound to the inert support medium. Okay, what is ion exchange? Reversible exchange of ions present in the sample with ions that are electrostatically bound to the inert support medium. The most important governing factor in ion exchange reaction is the electrostatic force of attraction, which in turn depends upon the relative charge. Okay, so the most important factor is electrostatic force of attraction, which depends on the relative charge, the radius of the hydrated ions, and the degree of non-bonding interaction. Okay, so electrostatic force of attraction is the major factor, but which depends upon the charge, the radius of the hydrated ions, and degree of non-bonding interactions. Ion exchange separations are generally carried out in columns that are packed with ion exchangers. Okay. Now there are two types of ion exchangers, an ion exchanger and cation exchanger. What is an ion exchanger? It's a inert insoluble support medium. Okay, it is inert insoluble support medium. This medium is covalently bound to positive ions in an ion exchanger and negative ions in a cation exchanger. They are called as functional groups. Okay. Ion exchanger is an inert insoluble support medium covalently bound to functional group. Okay. In anion exchanger, the functional group is a positive ion. In cation exchanger, the functional group is a negative ion group. Okay. Now see, as far as ions that are now to this functional group, counter ions are electrostatically attached. Okay, an ion exchanger first consists of an insoluble support medium to which covalently bound are the functional group. To the functional group, counter ions are attached. The counter ions are actually exchanged. Okay, so ions bound electrostatically to the ion exchanger are called as counter ions. See, the technique is extremely useful. In case of an ion exchanger, the counter ions are negatively charged. In case of cation exchanger, the counter ions are positively charged. Okay, so insoluble support medium attached with functional group attached with counter ions. Counter ions are electrostatically bound and counter ions are exchanged. Okay. The technique, that is ion exchange chromatography, is extremely useful in separation of charged compounds. Okay, even if the compound is uncharged, it can be made to acquire a charge by varying the pH. The value of the technique lies in the fact that conditions are so manipulated that some compounds are electrostatically bound to the ion exchanger, whereas others are not bound, they are removed. Okay. Now, you can see ion exchangers in this diagram, right? So, let us see this. So, the basic is this is a cross-linked, this is a polymer bead, you can say. This is a resin bead, you can see. Okay. You can see cross-linked polymers. The green one is showing the cross-linking. The red ones are the polymeric chains. So, there are too many polymeric chains which are cross-linked. So, this is a cross-linked polymer. The cross-linked polymer or the inert support is first attached to a negatively charged ion. Okay, as shown here. That is actually the functional group. Okay, to the functional group is attached a exchangeable counter ion, positive ion, you can see. So the counter ions are exchanged, the functional groups are fixed, right? So here in this, you can say resin, the counter ion is positively charged. So this is a cation exchange resin, right? So now you can see here anion exchange resin and a cation exchange resin, right? In case of an anion exchange resin, you can see the functional groups are positively charged groups. In case of a cation exchange resin, the functional groups are negatively charged groups, right? To this functional group, which is covalently bound, what we attach electrostatically bound negatively charged counter ions are attached, okay? To this anion exchange resin, counter ions are negatively charged, which are electrostatically bound, and they can be exchanged with the, you can say, analyte or sample to be separated. In a cation exchange resin, functional groups are stationary, they are attached, they are negatively charged ions, and the counter ions, which are positively charged ions, are then attached on the surface. They are electrostatically attached on the surface of the cation exchanger, which can be exchanged. Okay, so this is about cation and anion exchange resins, right? Now depending upon what your sample contains, what cation exchange resin or anion exchange, what your sample contains, whether you want to exchange cations or whether you want to exchange anions, you will be using either a cation exchange resin or a anion exchange resin. The exchanger is prepared in such a way that it is fully charged. Okay, the exchanger is prepared in such a way that it is fully charged. Right. The sample containing the ionic species to be separated is allowed to percolate through the exchanger. Okay. The exchanger is filled in a column, fully charged. Right. Then the sample which contain the ionic species is allowed to percolate through the exchanger for such a length of time which will be sufficient to attain the following equilibrium. What is the equilibrium? Now see, in this equilibrium reaction we have written E minus Y plus. That means E is the exchanger, okay? Y plus are the counter ions. What are Y plus? They are the counter ions, right? Minus, E minus means, okay, it is the functional group, and Y plus are the counter ions. If you add a sample which contains the ionic species X plus, then what will happen? When you pass the sample containing ionic species X plus, it will be exchanged. Now, it will be exchanged by what? The Y plus counter ions are exchanged by the X plus ions present in the sample. So, this is the equilibrium which is achieved, right? So, your exchanger contains, this is your exchanger which contains Y plus counter ions, right? They are exchanged by the X plus counter ions that are present in the sample, right? This equilibrium is achieved, right? Then where E minus is the cation exchanger, Y plus are the counter ions which are oppositely charged. Okay, so Y plus is the counter ion. X plus is the charged molecule present in the sample to be separated. The molecule can now exchange site with the counter ion as shown in the above relationship. That means Y plus are exchanged by X plus present in the sample. Okay? Now, if your sample contains a negatively charged molecule or it contains a neutral molecule, it will not be exchanged and it will be separated. Say for example, if your sample contains X plus and A minus ion, right? A minus will not be bound, will not be exchanged and can be separated. And X plus, which is positively charged, will be exchanged and retained in the column. This is how separation takes place. Okay, if you are using a cation exchanger, only the positively charged ions in the sample will be retained in the column. Negatively charged and neutral molecules will be separated. Now, once the exchange of counter ion with the sample ion has been achieved, the rest of the uncharged and like charged species will be washed out of the column. Okay. Now, the bound ions, okay, the sample ions X plus are now present in the column. So, we want to remove it. We want to take out. Okay. So, the bound ions X plus can now be eluted out. How? By percolating into the medium, increasing concentration of Y plus. How are you going to remove X plus? sample ions. Okay, they were present in the sample. You want to separate it. So they were first retained in the column. Now how they are eluted out? By increasing the concentration of Y plus. Okay, so that X plus are okay, because the Y plus concentration is more, X plus will be removed. Okay, or by increasing the pH of the solvent. When you increase the pH of the solvent, X plus will be converted. Okay, and hence converting the X plus into uncharged species. You increase the pH, X plus will be converted into uncharged species, and hence it will be easily removed. Now the concentration of Y plus required to elute out X plus, to remove X plus, will depend upon the quantity of X plus and charge present on X plus. The greater the charge present on X plus, the higher the concentration of Y plus will be required to elute it out. In the second case, you can simply increase the pH, and higher the pKa of X plus, the higher the pH required to elute it. Okay. Now, see in this diagram, right? This contains a cation exchange resin. Okay, you are shown a cation exchange bead having negative functional group and positive counter ions. So because the counter ions are positive, it is a cation exchange resin. So Y plus are the counter ions. Now you load the sample. You have loaded the sample. The sample contains X plus. The sample contains X plus molecules. So what will happen? When you add it into the column, the Y plus will be replaced by X plus. That means the sample ions, you can say component present in the sample X plus, have exchanged with Y plus and Y plus is removed. So the component of your sample which you wanted to separate, X plus, is now retained in the column. The next thing is you have to remove the X plus ions. How can you remove the X plus ions? Convert them into uncharged molecules. Convert them into uncharged molecules. How? By increasing the pH. Okay, and they will be easily removed, right? In the last diagram we have shown that we add excessive amount of Y plus counter ions such that they replace the X plus ions present in the sample. This is how sample ions X plus can be separated. This is how ion exchange chromatography helps you in separating the solute components, sample components. Okay. Not only that, the simple molecules are separated, but we can also separate proteins. Same procedure is applied for separation of macromolecules like proteins, nucleic acids having both positive and negative charge at different pH. See, the macromolecules can be made to bear more negative charge by increasing the pH, resulting in stronger binding to anion exchanger, or they can be made to acquire more positive charge by reducing the pH so that they strongly bound to the cation exchange. See, if you want to separate macromolecules like proteins, nucleic acid, they have both positive or negative charge at different pH. So, if you want to separate the macromolecules, then you can make them acquire more negative charge by increasing the pH, or you can make them acquire more positive charge by reducing the pH, and so on. Okay, so you can make the macromolecule a positively charged molecule or a negatively charged molecule depending upon how you are carrying out the separation, right? Now here we are going to discuss the separation of protein D in a mixture of proteins. There is a mixture of proteins, protein A, B, C, D, E, F, G, H, and all. Okay, from that if you want to separate only protein D, how can you do that? Okay, before that, you can see in this diagram, positively charged proteins bind to negatively charged beads. Positively charged proteins are how they are exchanged, how anion exchangers and cation exchangers are equilibrated, that we have discussed. Now how to separate protein D from a mixture of 7 different proteins. Okay, 7 different proteins. What are the 7 different proteins? Protein A, B, C, D, E, F, G. Okay, which one you want to separate? The protein D. Now, their isoelectric points are indicated. 5.2 is the isoelectric pH of protein A. Protein B having isoelectric pH 5.8, C having 7.3, D having 7.4, E, F, G 7.5, 8.6, 8.8 are the isoelectric pH. Okay. Now, all these proteins are added to a buffer which is having a pH 6.5. What will happen when you add them to a buffer having pH 6.5. So you can see protein A and B, they will become negatively charged. Okay, because their isoelectric pH is 5.2 and 5.8, they are uncharged here. Okay, when you mix all these proteins in a buffer with 6.5 pH, protein A and B will get a negative charge and they can be easily separated out by using a cation exchange resin. Simple. Okay, so first you put all of them in a buffer having pH 6.5, so that A and B acquire negative charge and the rest of them have a positive charge. C, D, E, F, G will have a positive charge. Now you pass them through a cation exchange resin. When you pass them through a cation exchange resin, A and B, which were negatively charged, will be eluted out directly. So now the mixture of 7 protein contains only 5 proteins. So you have to separate D from only 5 proteins. Okay. So now A and B, which were negatively charged, will be removed and you will have now C, D, E, F and G. So from this you want to separate only D. Now what you can do is, now place these 5 proteins in a different buffer. Say for example, the eluted proteins are added to a buffer with pH 8. Okay, now when you put it in the pH with buffer 8, what will happen? F and G will have positive charge, C, D, E will have negative charge, because your buffer is having more pH now. So F and G will get positive charge. Separate them by using an ion exchange resin. Pass them through an ion exchange resin and F and G will be directly eluted out because they will not be exchanged and retained in the column. So now what will be retained? C, D and E. Okay, so first you've passed them, made the buffer pH to 6.5, pass them through cation exchange resin. Now you increase the pH to 8, buffer pH to 8 and pass them through anion exchange resin. This is how you're concentrating. You're removing the unwanted proteins. Now your protein mixture is of C, D and E. Again change the pH and again pass through some ion exchange resin and your D protein will be separated. This is how, by altering the pH of the buffer by using either cation or anion exchange resin, the required molecule can be separated. Okay, now what are the different functional groups present in ion exchangers? Anion and cation exchangers. Anion exchangers generally contain aminoethyl or diethyl aminoethyl group or quaternary aminoethyl groups. Cation exchanger generally have carboxymethyl group or phospho group or sulfopropyl. These are the supporters. Now, there are different types of ion exchange resins depending upon their chemical nature. Strongly acidic cation exchange resin, weakly acidic cation exchangers, strongly basic and weakly basic. Okay, so whether they are strongly acidic cation exchanger or weakly acid cation exchanger, they have different functional groups on them. Okay, strongly acidic cation exchanger generally have sulfonic acid groups which are attached to styrene and divinyl benzene. See, two different types of resins can be used. Okay, polystyrene and cellulose resins, cellulose based resins can be used. Okay, so polystyrene and divinyl benzene are mixed and we get polystyrene. They are polymerized to get polystyrene. Weakly acidic exchanger, if it is, it will have carboxylic acid group and so on. Okay, SH group or phosphoric acid group, like that. If it's a strongly basic anion exchange resin, then quaternary ammonium compounds generally they are attached to polystyrene. Okay, if it is a weakly basic anion exchanger, then generally alkylamine groups, or you can say they are generally attached to the styrene and divinyl benzene copolymers. Okay, so strong cation exchange resins generally have you can say sulfonic acid groups. Weak ones have carboxylic acid group or maybe phosphoric acid, like that. Strong anion exchange resins generally have tertiary amines or secondary amines, and the weak ones have alkylamines generally. Okay? So these are the different types of exchangers depending upon whether they have a strong functional, strongly acidic group or weak acidic group, and like that. Now, ion exchange resins, two main materials are used for carrying out ion exchange. Okay, inert support. We are talking about inert support medium. Inert support. Two main materials, polystyrene and cellulose. Polystyrene is prepared by mixing, you can say, styrene and divinyl chloride, and they are allowed to undergo polymerization. Okay, so polystyrene and cellulose. Resins which are made from these materials, that is polystyrene or cellulose, differ in their flow properties, ion accessibility, chemical and mechanical stability. The two are totally different. Selection of the type of resin, whether you are going to use polystyrene or cellulose, depends upon the compound which we are separating. Polystyrene resins are useful for separating small molecular weight compounds. Cellulose based resins are used when macromolecule separation is to be carried out. Okay, so polystyrene resins are used when you want to separate small molecular weight compounds, and macromolecular separation, if you want to carry out, you are going to use cellulose based resins. Okay, so that depends what resins you are using, depends upon type of molecule you are separating. So as I told you, ion exchange resins for strong cation exchanger, weak cation exchanger. Okay, strong cation exchanger, what is the resin used? Sulfonated polystyrene or sulfopropyl cellulose. Right. If you are using weak cation exchange resin, then condensed acrylic acid or carboxymethyl cellulose. Okay. If you are using a strong anion, then polystyrene with tertiary alkyl group, you can say a tertiary amine group generally. And or diethyl quaternary amino cellulose can be used. If you want weak anion, then polystyrene with secondary amine, dimethyl aminoethyl cellulose or diethyl aminoethyl agarose. Cifadex can be used if you want a weak anion exchange resin. And the buffer, the choice of the buffer depends upon what separation is being done at what pH, whether it's a positive charged molecule or negative charged molecule, like that. So what are the various type of buffers we can use? Ammonium acetate buffer at pH 4 to 6, ammonium formate buffer at pH 3 to 5, pyridinium acetate buffer or pyridinium formate buffer, or ammonium carbonate buffer at pH 8 to 10. Volatile buffers are generally used. Okay, so, regarding the procedure of the technique and the applications of the technique, we will be discussing in the next video presentation. Okay.